Hi students, this is Mr. Bob, and in this video, we're going to talk a little bit more about nuclear reactions, and also we're going to start talking about energy sources, which is subtopic 8.1. So as usual, before watching this video, you should have some focus notes set up in your journal or notebook, and have a colored pencil or highlighter ready. And then about 24 to 48 hours after watching this video, there's some Oxford textbook pages that I will be putting in Canvas that you can go and look at to help you fill in, add, group, chunk, or highlight notes, and identify any points of confusion. Okay, so again, recommendations when you're taking notes during this video, please don't write down everything I say, actively listen and selectively write. Pause the video when we have sample problems, make sure you try and work them yourself first. That'll make your brain struggle, help you learn. And if you're still confused, please mark a point of confusion and make a point to ask a question of a classmate or get help from me. 3 essential questions for today. What's meant by the term critical mass when we're talking about a nuclear reactor? What is the difference between primary and secondary energy sources? And what's the difference between specific energy and energy density? Critical mass. So critical mass is what we talk about in nuclear physics when we think about what is required to sustain a chain reaction that we've been talking about, where again, out of a fission, at least one, or on average, one neutron goes on to cause another fission. There's a minimal mass that's required depending on the type of isotope you're using, how well they are enriched, which we're going to talk about that in a second, and the geometry. And so this minimum mass of fissionable, which is also known as fissile material, is that minimum mass that's required to sustain the fission process by itself. Okay, so if you have less than that mass, you're not going to have a critical mass. It's going to be subcritical, and you're not going to sustain a chain reaction. If you have more than the critical mass, then you will not only sustain the chain reaction, but you might actually accelerate that chain reaction. One thing that's important to note is that uranium-238 is what we call fertile, meaning it can occasionally fission, but it is not the type of isotope that is fissile, meaning it cannot by itself sustain a chain reaction. It's a different isotope of uranium, uranium-235, which is what we call fissile, okay? And so in order for us to have uranium fuel, like for use in nuclear reactors, what we have to do is we have to take the uranium that comes out of the soil, that comes out of the earth, and we have to enrich it, because over 99% of the uranium that comes out of the soil is uranium-238. A very small portion of it is uranium-235. But we need to enrich that uranium-238 in order to give it enough uranium-235 atoms, isotopes, so we can basically then sustain a chain reaction. One of the ways that we can enrich the naturally occurring uranium that's in the soil is by a process called centrifuging, which I'm going to explain here. So like I said, a reactor needs a higher proportion of uranium-235 isotopes than what occurs naturally. And so one of the means that we've discovered, devised, I should say, about how to enrich it is this thing called centrifugation. It's a really neat process, and let me just explain it here. If you look here, I just want to emphasize a couple things about this drawing. Think of this drawing over here on the lower right corner as like a big tube, okay? And you can see this tube has goes in and goes out. So notice what happens here, and this is really important. The uranium that they get out of the soil, what physicists do is they basically mix it, run it through a bunch of chemical processes, and they create what's called uranium hexafluoride. And uranium hexafluoride is actually a gas. So by creating this basically new compound, you're able to make it in gaseous form, and then you're able to feed it into the centrifuge. Okay, and if you've ever used a centrifuge before, you know what happens. You turn it on and it spins. And you can see down here, it shows that this centrifuge, this container is going to spin. Now, the other thing we have to remember, and this goes back to first year physics, if you think about it, more massive items, what are they going to do in a centrifuge? Well, if you think about it, the more massive items, they have more inertia. That means it's harder for them to change direction. So as the centrifuge spins, those more massive items are not going to be able to change direction to keep that spinning motion, as well as lighter items, okay? So the more massive isotopes, i.e. uranium-238, are going to move to the outside, to the outer edges of this spinning container. Whereas the uranium-235 isotopes, which are slightly lighter, are going to stay more in the middle here, okay? So notice what we do. We spin it, And then we provide an outlet for the stuff that's in the middle. And the stuff that's in the middle, like I just said, is going to have a greater content of uranium-235 than the stuff that's on the outside, because it's going to stay more central. And so what happens is this uranium-235 enriched gas is routed out of this centrifuge. And then where does it go? Well, basically it goes right back into one of these containers, okay? Because you have to do this a lot. Just one stage of centrifuging is not going to work. I don't know the exact number, but I know it's in the tens or even hundreds of centrifuges that you need in order to enrich the uranium enough so that you can get something that can serve as fuel in a nuclear reactor. And if you want to make a nuclear weapon, you have to even do this even further, okay? You have to do it to an even greater degree. Okay, so that's centrifuging, and that is one thing that I expect and IB expect you to know, just kind of a general idea of how the uranium can be enriched. Now I want to talk about energy sources, and this, what we're about to talk about here, comes out of the Oxford textbook. So as you saw in the first slide, I'm recommending that you look at the Oxford textbook if you can, sometime during this unit, to help you gain further understanding. First thing I want to talk about is primary versus secondary energy sources. A primary energy source is an energy source which is used to generate electricity or is used directly by a consumer. Okay, that's usually what we think about when we're thinking about energy. So examples of that, if you look here, there's a wood burning stove or a furnace. What does it do? It converts the chemical energy in wood or natural gas to heat your home, okay, or cook your food. And it does that by burning. Other examples of primary energy sources are the things you see there. They're the things we typically talk about: wind energy, coal energy, water, hydroelectric is when we say water, solar energy, natural gas, and nuclear power, which we've been talking about. So what's a secondary energy source? Well, quite simply, a secondary energy source is a source that has been transformed from a primary energy source before it's used by the consumer. And so the two examples that we have are electricity and hydrogen. And of those two, electricity far and away is the most common example of a secondary energy source because it's so conveniently transported and distributed. And it's easy for us to use. Okay, so you should know the difference between primary and secondary energy source and give some examples of each. Now go ahead and grab a calculator if you don't have one yet, because we're going to do a little calculation here based on two concepts. There are two important concepts here: specific energy and energy density. For each of the fuel sources I just mentioned, coal, nuclear, et cetera, they have what's called a specific energy and an energy density. When we talk about specific energy, that's quite simply how much energy you can get per unit mass of the fuel. And if you remember back to thermal physics, we had this specific heat capacity, which was the energy required per unit mass to change the temperature of an object. Well, this is the same idea. Remember, whenever you see specific, that usually means mass is involved. So specific energy means how much energy per unit mass from the fuel. So its units are joules per kilogram. Energy density is how much energy you can get per unit volume of the fuel source, and its units are joules per meter cubed. So let's walk through an example here together. We have a fission of uranium-235, and we know that it produces that amount of energy. And we know that the density of the uranium-235 is given there. And so what we want to do is we want to calculate two things. We want to calculate the energy, the specific energy, and we want to calculate the energy density. So let's walk through this together. Okay, and for this problem, we're going to assume all the nucleons in uranium-235 just have the same mass. For our purposes here, the mass difference between a proton and a neutron is not significant. So specific energy, if you remember, is energy per unit mass. Okay, so let's first of all figure out, let's go over to the side here and figure out how much energy is in how much mass is in one uranium-235 isotope, and therefore how much energy it would get if all that mass was converted to energy. So uranium-235, we know it has 235 nucleons. And we know that by what I just gave you, 1.007276 AMU per one nucleon. And we know what's true about the conversion from atomic mass unit to kilograms. This is something that is in your data booklet. 1.661 times 10 to the negative 27th kilograms is 1 AMU. Okay, so let's calculate that. When we do that, we get a number that is 3.9 times 10 to the 25th. So in other words, notice all this that I've done here is going right here in the denominator in mass. So the specific energy is, we know it produces 3.5 times 10 to the negative 11th joules. And that's divided by the number that I just got, which is 3.9 times 10 to the negative 25th kilograms. What does that equal? Oh, let me do this down here. Yes, it'll work best. The specific energy equals roughly 9.0 times 10 to the 13th joules per kilogram. Sorry, my penmanship is not the best today. So that's specific energy. And by the way, you're going to see in a second, that's quite a bit. Okay, now let's calculate energy density. So with energy density, notice we have, now that we have the specific energy, we can calculate energy density pretty simply. Because notice energy density is 9.0 times 10 to the 13th joules per 1 kilogram. And then notice the problem gives me the density, right? So I want meters cubed on the bottom. I don't want kilograms on the bottom. So notice if I just multiply the specific energy, the specific energy by the density of the uranium-235, notice kilograms cancel, and I'm left with joules per meter cubed. And when you calculate that in your calculator, you should get 1.6 times 10 to the 18th joules per meter cubed. By the way, I should have done this up here as well. Nucleon, nucleon, AMU, AMU, just to make sure we know what we get. Okay. All right, so you should be able to do that. If I give you a problem like that for any sort of primary energy source, you should be able to calculate the specific energy and the energy density. So let's see how the different specific energies and energy densities compare. No. Okay, there we go. This is from Wikipedia, and I think this is really interesting. And so if you look here, what we have is the different types of primary energy sources, okay? Stop, hold on. There we go. These are the primary energy sources for the most part. And you can see there we have a specific energy column and we have an energy density column. And if you just take a moment to look at it, just a couple things I want to point out, which I think are fascinating, is yes, look, all the nuclear stuff is got a specific energy and an energy density that is amazingly bigger, so much bigger than anything underneath it. Notice, just look, it's orders of magnitude apart. So this is why you can think and realize that there was a time period where people thought that nuclear power was going to basically solve the world's energy problems, right? There used to be a saying that electricity was going to be so cheap you wouldn't even meter it because you could just sell it for a flat fee, so to speak. That hasn't come to fruition for a lot of reasons. But anyway, you can see why the promise is there, or the possibilities there, given the numbers for specific energy and energy density. Also, I just want to point out all the way down here, at the bottom in terms of specific energy and energy density is batteries. And this is interesting, right? Because we use a ton of batteries in our world. And batteries are really useful to us because they're so portable and we don't have to be connected to the grid. But, and even though battery technology has improved quite a lot in recent years, it still struggles. It still falls behind, far behind in terms of specific energy and energy density. And that has specific repercussions or ramifications as we try and become fossil fuel free. Some of the biggest challenges we have are in the transportation sector, right? Something that no one's really been able to figure out in any concrete way is how to fly planes without fossil fuels, right? There are these electric powered planes are quite limited in their range. And that's largely because, notice here, they become so heavy when you weigh them down with batteries. So heavy, so much so that they can't fly anymore. So that's a big challenge, still presents a big challenge for us. And also heavy trucks. is another big challenge. You don't see electric powered heavy trucks, right? You see electric powered Priuses, passenger vehicles and stuff like that. And that's largely because we still have a pretty significant, these batteries are pretty heavy for the amount of energy they give us. Okay, let's talk about Sankey diagrams. This is another concept which is really useful. And so to do that, I want to walk you through kind of a funny and slightly unrealistic sort of engine, but it's really helpful. So suppose if you see there in the lower right corner, I've got a hot air balloon. The hot air balloon is hot because I'm burning some wood, okay? So if I want to convert heat to useful work, I have to use some sort of engine. This is going to be our engine for this demonstration. So the potential energy of a hot air balloon can be changed, right? Because look what happens, right? If you have a hot air balloon, boop, it moves up, okay? And so then if the hot air balloon moves up and then we kind of attach to the bottom to it a little water, a big sort of thing of water, right? Then what can I do? I can poke a hole in the bottom of that water and that water can fall. And notice at the bottom of the water falling, I can put a fan, and if it hits the blades just right, that fan will rotate. And if that fan rotates on the other end of that mechanism, I can produce electricity. Okay, I can create a little generator. So notice what I have here. I have an engine where I have a primary source, basically going through several energy transformations and creating, in the end, electricity, useful electricity. Okay, so so keep that in mind because we're going to keep this this example going here. So if you recall from first year physics, what is mechanical energy? You can pause the video if you want to kind of say it out loud for a second. But mechanical energy is the sum of kinetic plus potential energy, okay? Mechanical energy is the sum of kinetic and potential energy. All right, so there's a second law of thermodynamics, and it's really important, and it governs a lot of this energy production and energy conversion business. And it's got some hard limits on it. And here's one way to think about it. Certainly not the only way, and you'll see lots of mathematical ways, mathematically complicated ways to think about thermodynamics, especially if you continue in the science field. But this is useful. So one way of thinking about the second law of thermodynamics is asking the question, can all mechanical energy be converted to thermal energy? The second law of thermodynamics says yes, that is acceptable. But if I ask the inverse question, can all thermal energy be converted to mechanical energy? The answer is a resounding no. And so let's kind of talk about two examples. The balloon is one example that demonstrates this law, because if you think about it, the wood being burned, certainly it causes the hot air and the hot air balloon rises, but there is a lot of energy, a lot of mechanical energy that is converted into thermal energy during this whole process, okay? A second example, let's say I take a block and I push it along a friction-filled floor, okay? That's another example of where a bunch of mechanical energy, right? Mechanical energy meaning the sum of kinetic, and this is, let's just say it's all kinetic. All that kinetic energy, the block being pushed across the friction-filled floor, all that mechanical energy was converted eventually into thermal energy as the block came to a stop. But you know, have you ever seen a block just all of a sudden spontaneously start moving along a floor because all of a sudden it gained a bunch of thermal energy in it from the floor that's surrounding it? You haven't, right? And so that basically proves the second law, that you're never going to spontaneously get all thermal energy to be concentrated in an object in such a way that then it can be converted to mechanical energy without any losses, okay? So that second part is kind of what we're talking about here. And the example here is, again, you're not going to get all the heat that's been spread evenly across that floor. You're not going to get it all concentrated back in the block so the block can move again. Okay, so this comes up with the idea of energy degradation. And energy degradation is the idea that in any sort of process, a certain amount of useful energy is lost when the energy is converted from one form to another. So in energy conversion processes, this is true, and it's a term called energy degradation. And I would say this is one of those IB buzzwords, meaning that IB graders love to see this term thrown around whenever the question asks anything remotely associated with it. So I would strongly urge you to kind of write that down and have that in your hip pocket. And if you're ever an IB question, you're not quite sure what they're looking for, you might want to throw energy degradation in there and you might get a point. Okay, so now here we get to Sankey diagrams. And really, a Sankey diagram is quite simple. All it is it's diagramming out these energy conversions and showing how much energy, graphically showing how much energy is being lost through energy degradation at each of the conversion steps. So for example, with the hot air balloon, notice we have the chemical energy, which causes a change in potential energy, right? The balloon and the water that's held by the balloon. But not all of that chemical energy that wood burning is converted in potential energy. So this yellow arrow here shows the amount that's degraded, that's no longer useful. And then when the water falls, right, that potential energy gets converted into what? Kinetic energy. But again, not all of it gets converted. Some of it is degraded, and the yellow arrow represents that. And finally, the fan blade spinning, eventually some electrical energy comes out of there, but not all of the energy of this fan blades moving gets converted into electrical energy. There are some friction forces and some resistive heating forces, some resistive heating conversions of energy, which basically cause some thermal energy to be lost. Or I should say energy is lost in the form of thermal energy. That's what I mean to say. Okay, again, the degraded energy is represented by the yellow bent arrows and shows energy lost by the system. And so we can actually put numbers to this. And this is something I would expect you to be able to do, and I'd be expected to be able to do. If I give you numbers, can you calculate efficiencies? Okay, remember, who remembers what efficiency is? Pause the video if you can for a second, try and remember. Okay, so the equation for energy, if you remember, efficiency, excuse me, efficiency equals a couple things. It equals energy out over energy in. It can also equal work out over work in. It can also equal power out over power in. Those are three ways of expressing energy. Okay, so what is the efficiency of the first energy conversion? Well, all we would do is we would take the energy in is 100 megajoules, so the efficiency equals, this is 100 megajoules. And how much did we get out? 80 megajoules. So 80 divided by 100, that gives you an 80% efficiency. Question 2, what is the overall efficiency? So overall means at the very end, comparing the very end to the very beginning. So efficiency overall would be that 50 megajoules at the very end of the process coming out, divided by 100 megajoules, which is what you started with in the process, and you would get 50% there. Oops. Yes, efficiency is output over input. Okay, and again, I do want to emphasize that you can see IB questions where they put like these Sankey diagrams on graph paper with squares, and you have to count squares to kind of proportionally understand how much energy is being lost. So the size of the arrows is supposed to be proportional to the amount of energy passed through that process. It's supposed to be to scale pictorially. It can be sometimes. And just here are a couple of examples. Here's an example from biology, right? Consider a caterpillar that eats leaves. Notice the plant material eaten by the caterpillar, it's 200 joules that it consumes. And the question is, what is the caterpillar's overall efficiency? Well, in this case, just, you know, efficiency also means that goes to help the caterpillar grow, right? And so what you would see here is adding to the biomass of the world is the desired outcome. So the efficiency is the 33 joules, which is the growth divided by the 200 joules. And so it's only about 17% efficient. So living organisms are quite inefficient when it comes to these Sankey diagram type things, okay? Whoa. And then finally, another just biology. If you remember the power of 10, right? Every stage in sort of a consumer producer sort of ecosystem, from one stage to the next, only 10% of the stored energy gets used by the next stage, and 90% is lost in the environment. That's a big rule of thumb in biology that maybe you learned somewhere along the way. That's a Sankey diagram, or you could represent it as a Sankey diagram. Okay, finally, a joke. What is a wind turbine's favorite color? Blue. I know you're laughing. I can hear you laughing through the internet. Okay, so I hope you now understand what is meant by term critical mass. differences between primary energy sources and the difference between specific energy and energy density. Thank you.